All right, here's an example of Miner's and Manson's rule. This is problem 659 from Shigley, and I suppose I'm kind of cheating a little bit because I am using something that's already pre-written out, but I want to narrate through it. So in this scenario here, we have 306. We have a fluctuating leaf spring, which is, if you've ever seen a truck, right? You've seen the suspension underneath a truck. They have these are like plates that are held together right here, and they form. There's usually a U-bolt right in there, and they might have the shaft. One of the axles bolted onto this thing, and then this is onto the chassis. So this acts like a spring, and there's also shock absorbers in there to dampen it out. But this is the method that a lot of trucks use, especially on the rear axle. All right. This is a leaf spring, and it's a fluctuating stress that goes between 360 and 160, both in tension, and that happens for 80,000 cycles. And now the load changes to 320 in tension and 200 in compression. And they want to know how many cycles it'll survive using the Goodman criteria. They tell us the material is AISI 1020 cold drawn, and they have a fully corrected endurance strength of 175. So we don't have to use the Myron factors that have already been given to us. They do say to go ahead and assume that the this coefficient F that we usually use is 0.9, so we don't have to look it up. So we're going to use both the Miner's method and the Manson's method to assess how many cycles this thing's going to live. We look up in the back of the book the 1020 cold drawn steel, and we do need to figure out for both of these loading conditions what the equivalent completely reversed stress is going to be. So we figure out what the mid-range stress is and the alternating stress for these two loading scenarios. So you get 260 and 100 megapascals. And then from example 612, we use that Goodman rewritten equation to try to see where it has that intersection. So this is the equivalent completely reversed stress for this loading condition. We do the same thing, but this time we have 320 and we have a compression right there. So our mid-range is considerably lower and our alternating is considerably higher because we have the minus, and so we end up with 60. But both of these are in tension, by the way. And then we have completely reversed. By the way, if either one of them, if the alternating was in compression, then we would discard it, because that doesn't count. If you remember way back, that alternating stress, that if it remains in compression, the cracks don't open up, and therefore the alternating doesn't factor into things. So the completely reversed stress is now a little bit larger, 298. So what we do for Miner's rule is actually pretty easy compared to Manson's method. First off, we do need to find what capital N1 and capital N2 are going to be. So in order to do that, we need to find the coefficient and exponent for the equation that looks like this right here, right? Because that describes the line that's going to intersect for the thing. And by the way, in both of these cases for the completely reversed stress, you notice that that's larger than the endurance strength. So therefore, in either order, they would fail, right? Or eventually fail. It's not going to be infinite life because it's greater than the endurance strength. So we're able to find, plugging in the numbers that we get for that F and the ultimate strength, and the endurance strength, we're able to get what the coefficient is going to be, the original coefficient of the original line, and then we're able to find what the slope of the original line is. Now, I'm tempted to actually use subscripts of 0 for that to represent that. So that could be a little confusing. I might have changed my mind at some point and say there. Because this is the original one that I put in there. But now we want to find what the life is going to be at that stress level, right? So that original stress level for the average event, it would live that long if that's the only stress that it had. And the same thing true for the second stress level. It would live this long if that's the only stress it had. So it would live like maybe close to 150,000 cycles at the initial stress. At the new stress, it would only live about 15,000 cycles. Now we figure out like how many cycles left would be after the first event, because it was supposed to last 150,000 cycles, but we used 80,000 of them up. So what's left is right around 66,000 cycles are left. Using Miner's rule right in here, okay, and actually we didn't need that last step before using Miner's rule. The very simple Miner's rule, we just rewrite this and find out little lowercase n2 is going to be, and that's just really just subtracting out the damage fraction. That 80,000 divided by that original number of cycles that it could have lasted, that's the percentage. So that might even be kind of like a little bit of an interesting thing to us to take, and take 1.459 E5. So it actually used up, right here, it said our initial loading used up 54.83% of the thing's life. So what was left was only 45% of the thing's life, right? And so you multiply that 45 by the possible number of cycles that it could have lived if it hadn't already experienced that initial loading, and you end up with 7,000 cycles. As a graph of the thing, right, we take this initial loading. No, the initial loading is down here, right? So it's like somewhere right in there, right? So this is the 224 really. And here's the 80,000. So you could actually see the 80,000 actually leapfrogs over, right? Because if we went all the way across over to here and down, this is where the N1 is going to be, right? So we could see that that's a larger value right in here, picking apart the values. You see the N1 is 150,000 cycles, so that's where right about that's going to be. We take that, and what's left over is the 66,000, and so that ends up being right here where that blue line is going to be, so or blue dot is going to be. So that's where that one is. So we draw a new line that runs through there. That's what we did, or that's what we could do later on. Okay, so we're not doing the mathematical equation for the Miner's rule. We don't need to in this case. I do that in a different example. But what we find is that this 7,000 actually comes in when we hit that 298 right there. That new stress level comes down, and that right there is going to be where the N1 is. Now compare that to the Manson's method, which requires a little bit more effort numerically, because we're going to create, in order to get the new equation for the new line, we need to get both a coefficient and a slope. So what we do is we plug in the 2 points that we know. We know that point, and we know that point right there, right? So here's the coordinates of that point that we knew up above, or here. So here they are right there. And then we also knew that F times SUT, and we also know that it's at 1,000 right there, right? So there's the other point. So putting those two into these equations, of course, but we were dividing those equations by each other, and we noticed that the coefficients drop out. That's useful. Then we take the log of both sides of this so that we could pull out that new coefficient. That's the new slope, excuse me, the new slope of B. Just rearrange this thing, and we get a negative number, which is what we expected. And because you could even just think of that as being a negative slope, right? That's one way you could think of it. And then if we want to get what the A is, we just go ahead and plug in this point right here, right? Plug in those values right in there, and we solve for that A2. So now we have a coefficient and a slope for a new line. So now what we do is we take the inverse equation right there, and we figure out how many cycles is going to last at the new split, and we find out that it's 10,000. If we take a look up here, where that intersects right here, that 298, it comes out right to 10,000. So there you go. There is the process, the big idea, and the method about which going through there. And hopefully you can kind of get your head around, the big picture, but also kind of see the little intricate details in trying to work through the thing. So I believe that is 10 minutes of your life that you're not getting back.